power series is really just an infinite polynomial, written as the sum of c sub n times open bracket x minus a close bracket to the n. It only converges for x within a certain distance of a, and that distance is called the radius of convergence, r, which we usually find using the ratio test. The Taylor series of a function f centered at a point a is built entirely from information at that one point. It's the sum of f's nth derivative at a divided by n factorial times open bracket x minus a close bracket to the n. When we center at a equals 0, we call this special case a Maclaurin series. There are a handful of these you should recognize on sight. The series for e to the x, sine of x, cosine of x, and 1 divided by open bracket 1 minus x, close bracket. Now let's work through an example. Find the Taylor series for the natural log of open bracket 1 plus x, close bracket, centered at 0, along with its radius of convergence. The key insight is to recognize that the natural log of open bracket 1 plus x, close bracket, is the antiderivative of 1 divided by open bracket 1 plus x, close bracket. So instead of finding this function's derivatives directly, we'll build its series from that simpler function. We rewrite 1 divided by open bracket 1 plus x, close bracket, as a geometric series, the sum of open bracket negative 1, close bracket, to the n, times x to the n, and this is valid only when the magnitude of x is less than 1. Now we integrate term by term. Integrating each x to the n gives us x to the n plus 1 divided by n plus 1, and after shifting the index, this gives us the natural log of open bracket 1 plus x, close bracket, equals the sum, starting from n equals 1, of open bracket negative 1, close bracket, to the n plus 1, times x to the n divided by n. Since integration doesn't change where the series converges, the radius of convergence is inherited directly from the geometric series step, giving us r equals 1. Here's the trick worth remembering. Rather than grinding through higher and higher derivatives directly, which gets messy very fast for a function like this one, it is almost always faster and less error-prone to build the series from a known Maclaurin series using substitution, differentiation, or integration. Now, the most common trip-up. After finding the radius of convergence, students forget to check the two endpoints of the interval separately. The ratio test is inconclusive exactly at those two boundary points, so each endpoint needs its own fresh convergence test. So here's the teaching tip. Always treat finding the radius and checking both endpoints as two completely separate mandatory steps, never combined into one. Substitute each endpoint value into the original series individually and run a fresh convergence test on each one at a time.